Hello everyone, welcome back to the channel. I hope you guys are doing really great. So let's see today's daily challenge on Leetcode and we will try to solve it together. So yeah, today's challenge is a moderate one. So let's try to understand the problem statement today at first and then we will continue with the video. Uh, there are some robots and factories on the x-axis. You are given an integer array robot where robot I is the position of the ith robot. You are also given a 2D integer array factory where factory j is a pair which is nothing but position j and limit j, which indicates that position j is the position of the jth factory and the jth factory can repair how many number of robots. Okay, at most it can repair limit j number of robots. The positions of each robot are unique. The positions of each factory are also unique. And note that the robot can be in the same position as the factory initially. All robots are initially broken and they keep moving in one direction. So basically, you need to repair all these broken robots. And once they are repaired, it's like they vanish. Okay, you do not need to think what happens to them after they are repaired, like they get collided with other robots or anything like that. You do not need to think. The details is given in the question that the direction could be negative or positive. When a robot reaches a factory that did not reach its limit, the factory repairs the robot and it stops moving. Okay, at any point you can set the initial direction of the moving. For some robots, your target is to minimize the total distance traveled by all the robots. Okay, so you want to repair all your robots which are initially broken, and in the process you want to see what is your minimum distance. That will be okay. And return the minimum total distance traveled by all the robots. The test cases are generated such that all the robots can be repaired. So it's not like uh, all the robots cannot be repaired. So basically, the count of the total number of robots should be less than or equals to the sum of limits of all the factories. I hope you do understand what I mean by this. So one factory can repair at many limit number of robots. So sum of all the limits of all the factories should be greater than or equals to the total count of the robots. So you also note that it's told that all robots move at the same speed. If two robots in the same direction, they never collide. And even if they are in the opposite direction, they also never collide as if they cross each other. And if a robot passes by a factory that reached its limit, it crosses as if it does not exist. Okay, and if the robot moves from position x to y, the distance is traveled, it is y minus x. So yeah, that is all. You can see this example. These two robots are moving. So see, robot number 0, 4, and 6 are there. Number 6 is can be repaired by the factory at position 6, so it does not need to move at all. Okay, now and you can also make these two robots to be repaired by this factory number 2. Okay, this factory number 2 has a capacity of 2 limit, so it can repair both of these robots, and in the process this robot will move 2 distance and this will also move 2 distance. Total will be 4, which is your answer. Okay, I hope that is very simple, but this example tells you nothing. So you try to take some example and try to write down some observations. Okay, as we do in every problem, we try to understand and we try to write down some observations of what we see in this problem. Okay, so on an axis, you have some robots, okay, and you want to repair all those robots, okay. So you have some robots and you want to repair all those robots. For repairing them, you have some factories also, okay. So yeah, I'm denoting the factories like this, and you want to make the robots move to the particular factories, okay. So you want to make the robots move to the particular factories. Now, if you notice one thing that if you see from the view of factories, you can say that a particular factory will always repair a segment of some robots. Okay, so there can be actually not just this, there can be many robots, right? So one thing you can tell that one factory can, based on its limit, it can repair a segment of robots. So let's say this first segment is repaired by this particular factory, and let's say this second segment is repaired by this particular factory, and these all of these segments is also repaired by one particular factory. So if you try to write down this observation, what is this? That uh, a factory repairs a segment of robots. Segment of by this I just mean that a continuous segment of robots. Okay, by segment I mean the continuous segment only. And yeah, one thing is that you need to process them in order, let's say from left to right. So they all must be sorted by position. All must be sorted by position. So this thing you can easily take care of, right? So all of them, you must take care that they are sorted by position. So yeah, these two things are our initial observations. Now, can you think greedy work? Okay, can you think greedy work? So by greedy, what I mean that I just pick up a factory. So uh, how will a greedy type of solution look like? I just pick up one factory. So pick a factory, okay, which you want to repair. See, I told that I'm iterating factories. Okay, I'm seeing the from the point of view of factories, and I want to see which factory can repair how many number of robots. So I pick a particular factory, let's say it's the IS factory, and I want to greedily, so let's say it has 5 limit, it can repair 5 robots. Okay, it is at some position cause I, let's say, that doesn't matter, but it can repair 5 robots. Now I select nearest 5 robots. Since we need to minimize the distance, we select the nearest 5 robots and repair all of them. And repair all of them. So this will be our greedy algorithm, right? But do you think this will work? Can you tell me a particular case? Can you draw one particular case where it will not work? Okay. You see, if you try to say that, hey, I have this factory and this factory, okay? And for me, the 5 robots are something like this. So I am selecting these 5 robots to be repaired by this particular factory. But you see, this robot is closer to the distance of this factory than this factory. But still I selected this robot in my greedy algorithm. So maybe I should leave out this robot. And even if I have 5 limit number of robots which I can repair, I should restrict myself to some lesser value. Let's say to 4, to 3, or to 2, whatever. Okay, and I should maybe make this that choice that I should leave out this robot for this particular factory, and then this factory, according to its limit, will end up in repairing that robot. Okay, but they must be continuous segments, and those things hold true. So you see, what I'm trying to say is that you get some choices, right? So it might also be possible that one factory did not repair any robot, or one factory repaired one robot, two robot, three robot, limit number of robots. Okay, so there are multiple of choices which you do. So whenever you get choices, of course you can try by recursion and memoization and following recursive followed by recursive DP or memoization, whatever you call it. So yeah, whenever we get choices, you know that, right? Let's say take not take, you get choices. Take not take kind of DP. There also you have choices. So similarly here also, whether how many number of robots a particular factory will reduce, you try to get a choice. So that's why you will try to use DP for solving this problem. Now yeah, we will try to write a recursive solution at first, and let's see. Okay, so yeah, I hope you know how recursive solution works. There are two things here, factories and robots. So of course it will be a 2D DP, and both will be initially 0, 0. And you will try to go through all the factories and try to, for the ith factory, will try to repair a sub-segment of robot. Okay, so that's what you are going to do. So at very first, what you are gonna do is sort the robots quite obviously, as well as the factory. Robot dot begin and end, right? So we have sorted the robot. Now we want to sort the factory also. So yeah, and what is the factory? The first position in this factory is position, and limit I want to sort by position only. So if I just write the sort function, it will automatically sort it by the first position only. So first element, which is the position. So that's why I do not need to worry for that. And yeah, what I can do is I can write another function recursion, which will just calculate total distance. So let's say I can write this calculate function, uh, which will take input as robot. It will also take the input as factory and 0 comma 0 initially. Why 0 comma 0? Because initially I am at the index of the 0th robot and I am at the 0th factory. Okay, I want to start solving for them. So yeah, that is all. And as define, I will be using long long again and again since the output is long long here. So uh, let's see. LL calculate. Uh, we have a vector, and we also have a vector of vector, which is nothing but the factory, right? Okay. And for this we have R, let's say, as the robot dot size, and also let's say for F we have factory dot size. So these many number of factories and this many number of robots are there. I want to iterate through the factories as well as the robots. So we have two more integers, right? 0 0. So it will tell you the which index of the robot I am currently at and which index of the factory I am currently at, right? So R index and F index I can tell. So both are initially 0. Uh, yeah. So first of all, in we are writing a recursive solution. So we must look for the base case. So what will be the base case when this index or these factories are reaches the last value? So we are at first we are trying to iterate by factories. So if in case we see that f ind reaches to be f, then you return 1e18. Why 1e18? Because we want to minimize your total distance, right? And we are finished with all the factories, assigning with all the factories, and we are at a non-existent factory, right? Uh, we are at f index equals to f. That means the element after the last element. So I just return 1e18. So in order to minimize the our total thing, and if what happens, if the R end happens to be equals to R, I should return 0. Why? You might be thinking, in order to minimize, why I'm returning 0? Because you see, when will R index reach R? We will try to see that robot, what is the this when see, with this example, with this argument R in, I am trying to see how much distance this robot has to move to go to the current factory, right? So for a non-existent robot, so the robot after the last robot will contribute no value. Okay, so this is not that I am returning as my answer. This is as if I am adding the distance value to my answer. So distance moved by the robot after last robot is 0. The robot after last robot, it doesn't exist, and therefore it doesn't move any distance. So we do not need to add any distance to it. Okay, we do not need to add any distance to it. I hope this is very very clear to you now. Okay, so yeah, now we can extract the limit and the position. So what is our limit for this ith factory? So it is nothing but factory of I extract this particular index and go to number 1. Why? Because it is the second element, which is the limit, and the first element is our position. So again, factory of f index and 0. Okay. Now again, what was our choice? That see, a particular factory can repair 0 robots, 1 robot, 2 robot, all the way till limit number of robots. So I will try to see how many can I actually reduce. Okay. So repair. So for, let's say, J, try to repair J robots. Try to repair J robots. Okay. J can be 0. Okay. J should be how much? R int. Okay. Plus limit at max. See, you are at a position of R int and not 0, right? Then this should also be R int. And one thing you must always take care that you should never exceed this. So J less than R also, and this. So I hope you do realize what I'm trying to do. I'm trying to repair J robots based on the limit value. So let's say I am at R int. It means that all the indices before this, I have already repaired those robots by some factory or the other. So now from the current robot onwards, till the limit number of robots, I can repair, I can try to repair, okay? And I must make sure that J does not exceed R, and that is these many number of robots I will just try to repair, okay? Yeah, so that is the thing. So this particular robot, so try to repair 0 to limit robots, okay? Not 0 robots, 0 to limit robots, and J is the index number of the robot which I'm trying to repair. That is what. So yeah, I hope you do understand, and there should be no confusion in this. Yeah. So now obviously what I will try to do is try to calculate the cost, that how much cost did we incur in reducing all these robots, okay, repairing all these robots. So yeah. Uh, so how should we calculate the cost? You see, uh, limit can be again anything. Try to repair 0 to limit number of robots. Limit can be anything, right? So we need to vary that also. So for int I equals to 0, I less than or equals to limit, right? I plus plus. This thing I was forgetting, that this needs to be on an outer loop. Why? Because I need to try this many limit, right? Try to repair 0 robots, 1 robot, 2 robot, all the way till limit number of robot. So try to repair I robots. I'm trying to repair I number of robots. Okay. And then only I will try to see that what is my total cost for reducing this many number of robots. So yeah, that's how I remembered. So I hope you got it. And which all things do I need to be doing in long? This cost, I guess, should be in long. So yeah, whatever be the case, cost, we can just add it to be plus equals to absolute value of uh, the particular position, and okay, this position of the factory and minus the position of the robot. Factory robot needs to move to the factory. So whatever we do, position minus robot of which robot I am trying to repair? This jth robot. So that value we just add it to our cost. So in this way, we just calculate our total cost and try to minimize some answer. Okay, so answer will be nothing but minimum of answer and cost plus now I need to write the recursive function. So calculate of robot factory R end. What will be R end? You see, I have uh, repaired this robot. Okay, so from next robot onwards, I can try to see uh, how much I want to repair. Right? See, starting from R end, I have repaired all the way till these robots. Okay, so now whatever my J value is, from that index onwards, I can try to repair my robots. So this J index we need also, right? This J index we also need it. So yeah, uh, since I need it, I will try to write it and in a different place. Okay, yeah, you do not need to initialize it here. And yeah, now you will have this J variable saved. So J variable is basically iterating from our end, and if it is trying to repair these many number of robots, and after this has repaired, whatever the value of J, from that value of J onwards, I will try to have this robot index, right? Because uh, if I, let's say, this particular factory stopped at repaired these many robots and stopped at repairing this robot, so J will be after J plus plus, J will point to the next robot, and for the next factory we can go ahead with repairing the next robot with this value of J. I hope you do understand. Okay, this is not much difficult also. So, and I will go to the next factory, that is F index plus 1. So yeah, that is the way we can just minimize our answer. And what else? We can just return answer. Uh, we will also try to write the DP, but before that, we will try to see whether we are getting a proper TLE kind of thing or not. Let's try to see if it works at least for some test cases. Okay, so I did not declare answer only. So yeah, I need to do it, and that answer should be, let's say, 180. Okay, or int LL max should be perfect if you do it. So yeah, that is it. So let me try to index of invalid argument. Why am I getting this error? So R int equals to R distance moved by this particular robot. Okay, let's try to run now and see. Yeah, you get the accepted. If you try to submit, you see you will most probably get a TLE. Yeah, you see you got a TLE because this is an exponential runtime complexity, right? So you would want to catch it or memorize it. And I hope you already know how simple it is to memorize this. And you can just use a DP, okay? Recursive DP we call it. And how to convert a recursion to recursive DP, I have explained multiple times in my previous videos as well as in my DP playlist, which is there. So yeah, I will just try to do this. And we have RF, and we will try to initialize our DP also. So, and that way, DP must be, we must remember to make long. Yeah, and R plus 1, because the robot dimension is I, which I want to take, and the J second dimension which I want to take is F. Okay, initially all are -1, and I will like to pass this DP. And wherever I am calling this recursive function, I need to pass it. Okay, yeah. So after I have passed it, yeah, as you know, what we do in this recursive DP conversion is that we try to check whether this DP position has already been filled. So it is initialized by -1. So if it is not -1, it means that it has already been filled. So if DP of R index and F index is not equals to -1, it means that if it is already been filled, do not recalculate the same thing again. You can just simply return DPR index and F index. Okay. And not only this, you must also save your state. R index, F index. Every time you save your state, and whenever you are encountering a duplicate state, do not recalculate the whole thing again. This makes sure that you always end up in filling all the cells of the DP. Okay. You do not end up in calculating this m into n number of times, where m into n is the dimension of the total DP. Okay. Your calculation number of calculation limits gets clipped to that value. So yeah, that is all. I will try to submit it for 2 test cases first and check it. Yeah, it is working. Let's try to submit it for all cases. I hope it should work perfectly fine. Yeah, it does work. We have a decent memory complexity, but not so good runtime complexity. How to improve it? You can try to convert this to an iterative solution. Okay, this is a recursive DP. You can try to convert it to an iterative DP and check uh, whether the time complexity is improving or not. I think it should improve. But yeah, it does give the accepted. You can follow my DP playlist for the particular method of how to convert from recursive solution to an iterative DP. So that's all for this video. I hope you will be able to do that much optimization on your own. So yeah, I hope at least the concepts and all were very clear to you. If you have any doubt, you can definitely ask me in the comment section. So yeah, that's all. I will meet you in the next video. Thanks a lot.